Hi, in this video, we want to take a look at systems of equations and generalized inverses. Okay, so with a system of equations, what we've got going on is we have a bunch of linear equations. We have one or more unknown variables. And so what we'll have is, let's say we have n equations, they're linear equations, and p unknowns. And so what we can do in terms of matrices, we can represent it as, let's say this is my first equation. I have A11 is the first coefficient of the first equation. So subscript 1 tells me it's the first equation. Then the 1 tells me it's the first unknown. Then A12, first equation, second unknown. A13 is first equation, third unknown. Down to A1P, first equation, pth unknown. All right. Now, when I look at the coefficients at the bottom, AN1 is nth equation, first unknown coefficient. AN2, nth equation, second unknown coefficient. So when I say unknown coefficient, I mean the coefficient of the unknown value. Then ANP is the nth equation, pth, the pth coefficient of the unknown, or pth unknowns coefficient. All right, so, and then the x's, x1, x2, x3, all the way up to xp, those are our unknown values. And then we have c1, c2, c3, all the way to cn. So what we're doing is that I can put this into matrix notation of A times vector x is equal to the vector c. A is an n by p matrix, and it's known. All the values are known in this situation on A. For C is n by 1, and it's known. So remember, we have n equations. Now the vector x is a p by 1 vector, and all of its values are unknown. So A is an n by p, all its values are known. C is n by 1, it's a length n vector, and all of its values are known. But x, when we're solving the equations, we're trying to find out what the x values are. We're trying to find our x, like somebody who's like really broken-hearted over being broken up. We're trying to find our x. I hope that was funny. I think it was funny. Okay, if A is square and non-singular, then automatically we have a solution, and it's unique. There exists a unique solution. All right, now that solution is going to be the x vector will equal the inverse of A times the vector c. Boom, we've got it. And to see that, just multiply both sides of this equation by the inverse. You get the I on the left. I times x is x. And then we have A inverse times c. Boom, we've got it. Okay, so think about your college algebra days. We had the term consistent way back when. Consistent means one or more solutions exist. In this situation, either one or infinitely many solutions exist. That's how it will always work out. It's either 0 solutions where it's inconsistent, 1 solution, or infinitely many solutions when it is consistent. Okay, so consistent means there is one or infinitely many solutions. If there is no solution, so there's no x's that solve this, then the system is called inconsistent. All right, now we've got a theorem for us. The system of equations, A times x equals c, has at least one solution if and only if the rank of A is equal to the rank of A when I append the c vector onto it. Okay, proof. So this is if and only if. So I've got two directions. The one direction, I make the assumption, my hypothesis is that this equation has at least one solution. There may be infinitely many x's, there may just be one. We don't really care. I use that piece of information to prove that the rank of A is equal to the rank of A appended with C. The other direction is that I'm going to assume by hypothesis that the rank of A is equal to the rank of A append C. And then I use this piece of information to prove that this system of equation has at least one solution. Okay, so we're going to go from left to right. I'm going to assume that this part is correct. I need to show that this part is correct. So we're going to say that x is a solution, any solution. I'm just saying that I have x is a solution And I'm going to treat it like it's a concrete known value. It's no longer a variable for the purpose of the argument. All right, so ax equals c implies that if I subtract c from both sides, I'm going to get the 0 vector. Okay. Now let's think about this. Well, what I could do is I could represent this using matrix multiplication to factor out. So it's like I've got x times a, and I've got -1 times the c vector. If you think about matrix multiplication for a bit, what I could do, I could say that this is a append c times the vector x with -1 tacked on to the end of the vector. All right, so then I know that this has to be equal to 0. Well, okay, whoa. Think about that. I have matrix times the vector equal to 0. Something needs to like go woo, woo, woo. You need to spot something. Something needs to go off in the back of your mind. Something like linearly dependent, linearly independent. All right, what we're saying here is that there is a non-zero vector that when I multiply a append c by that non-zero vector, I get the 0 vector. Off the top of your head, you need to go, hey, that's linearly dependent. Okay, it's a linearly dependent. This is exciting. We got some good stuff going. All right, so we know that this is a linearly dependent matrix. That means that C has to be in the span of A, some way, some shape, some form. All right, so this means that the rank of A append C is equal to the rank of A. Now that I look at it, there's a little bit more I should have fleshed out right here. I should have talked about why this equation gets to here. Now I'm looking at it, that I can see that there's kind of a gap conceptually, but because this one coefficient of -1 and C is equal to this, that means that C has to be in the span of A, which means that C does not add to the rank when I tack it on to A. Therefore, boom, we've got it. All right, now we're going to go the other direction. So I'm going back up to the original statement. Now I'm going to make the assumption that rank of A is equal to rank A append C. So this is my hypothesis, and I need to use this to show that this system of equations has at least one solution. All right, so by hypothesis, rank of A is equal to rank of A append C. Okay, so that tells me that the number of linearly independent columns of A is equal to the number of linearly independent columns of A append C. Okay, now tacking on columns onto a matrix will can only increase the rank. It can't decrease it. Okay, but if it stays the same, so if you think about it for a moment, all the columns of A are contained in the columns of A append C. Okay, but the number of linearly independent vectors did not increase. So it didn't increase. Therefore, we know that C has to be inside the span of A, because tacking it on does not increase the number of linearly independent columns because of the rank equality. All right, therefore, there has to exist some vector where if I multiply A, I get C, because C is inside the span of A. There's some nuance into this. You might want to look over this a few times before you start hitting the homework. All right, if I was to say one concept, just one concept that you need to know mathematically to get good at data science, I would say the number one concept you need to have in your head is matrix algebra. If I was to go deeper in matrix algebra, linear algebra, I don't really care which one you worry about. I'll say matrix algebra because we're keeping it real, because we're dealing with real numbers. After matrix algebra as a whole, if I was to say one concept within matrix algebra, I would say systems of equations. It's super, super important for a lot of stuff we do. It is absolutely critical to getting good results in data. If you don't understand systems of equations from a matrix point of view, you really don't know what your algorithms are doing. You can't understand it. It's kind of like a prerequisite. Like, you know, for a lot of data science algorithms, understanding systems of equations is like understanding the alphabet to being able to read, you know, be able to write your dissertation. It's a first step. You got to get it. All right, the next concept I want to talk about is a generalized inverse. Okay, if you were to take a theory class as an undergraduate, your class probably didn't even touch this concept. A lot of the proofs that we're going to be going over, you could skip a lot of details and make it a lot easier if you assume that you have full rank every single time you move through. That's how it was when I was an undergrad. Well, in real life, we get into situations where we don't have data as nice as we would like. The generalized inverse, what this does for us, this enables us to solve linear equations when we do not have full rank. And so this will be important to us when we have data vectors that are within the span of other data vectors. All right, so the generalized inverse of A is any matrix A superscript negative sign such that A, generalized inverse A, is equal to A. Okay, pause for a moment. First thing I want you to do, I want you to think about regular inverses. First and foremost, if A is a square non-singular matrix, meaning it has an inverse, if A has an inverse, meaning it's square, then the generalized inverse is equal to the regular old inverse. So anytime you look at a theorem, anytime you don't know what's going on, the first thing I want you to do when you talk about generalized inverse, look at the special case where A is a non-singular square matrix, and then look at the regular old inverse, and then understand the proof there, then progress to the generalized inverse. Okay, so if I was to look at this, if A is non-singular square, then A superscript negative sign is actually the regular old inverse, which means that this part is equal to I times A is A, so it's stupid. It's a meaningless equation if A is non-singular square. Now, and so another thing about this is that if A is invertible, then the generalized inverse is unique because the inverse is unique. Now, if A is singular, that means it does not have an inverse. Either that's because of its dimensions, or it's square and low rank, or it could be both, you know, the dimension and low rank. Then the generalized inverse is not unique. This is something that is going to be important. It's not unique. That means that there are multiple versions that will satisfy what we're doing. Okay, so if A is n by p, then A generalized inverse is p by n. And if you look at this equation, that's the only way that you can go n by p on the left, n by p on the right, and get n by p. This is the only way it works for matrix multiplication. All right, let's look at a theorem. If A is n by p, the rank of A is R, and A is equal to this block matrix, and A11 has rank R, then one of the generalized inverses is going to be the block matrix in the upper left-hand corner inverse, and then the rest are zeros. Okay, so let's pause for a moment. Let's think about this. If the rank of A11 is R, then that means that when I look at across here, when I look at all the rows on the top blocks, then A12 has to be in the span of A11. Now, if I think about this way, if I think about the columns, or excuse me, if I think about the rows going this direction, having rank R on A11 means that all the rows in A21 have to be in the span of A11. All right, so there's a lot of stuff going on. And so really, these guys are just dead weight for this purpose. Now, remember that if R is less than the dimensions of A, and A is non-square, then there are multiple generalized inverses. This just gives us one possible one to work with. Makes our life easier. Now, this is a special situation. A may or may not have this form of a block matrix. All right, proof. Okay, so if A is R by R, then A is equal to A11, and because the rank is equal to the dimensions, it just works out. It's stupid, it's trivial, it's nothing. Okay, otherwise, all right, so now we're gonna say that there is some part of A that's not captured by the A11. Okay, so basically how this proof works is that the author of the textbook gave us a way to actually find it. It gave us an equation. So this is a constructive proof. Now, one thing that's nice about this is that we can see how we can use this to get the generalized inverse from the proof. That's good. The bad part is, like, you really would not generate this on your own unless you've spent some good time on this problem. Okay, so let's go ahead and just let's just go ahead and say that A superscript negative sign is equal to this. Then if I go through, I go A, generalized inverse A, and we haven't proven that's a generalized inverse yet, but I'm just gonna say it that way because it works out. A, if I write this out, it's gonna be in this format. Okay, so now I can go through and I'll do matrix multiplication. There's a special formula in chapter 2 for me to multiply these two. Fortunately, there's a crap ton of zeros. Zeros are nice to multiply by. This makes it a lot easier. So boom, I get this. So these two multiplied using the formula becomes this. Okay, so now I'm going to use the same formula and multiply these two together, and I get this. All right, now, just let you know, before I do any of the proofs, I write them out myself. Then I look at the author to see if the author has a better way of doing it. When I got to this point, I thought I made a mistake. No, there's no mistake. This is correct. I remember when I got to here, I was like, oh, crud. It's just simplified. And I redid it, switch the order of the multiplication. It was a waste of my time. I was right. I looked at the author's proof and went, oh, okay, I see it now. So we need to show that this lower right-hand corner block is equal to A22. Once I've got that, I'm done, because then, so if I look at this, we've shown through these two steps of matrix multiplication that A, generalized inverse A, and A is equal to this. By hypothesis, A is equal to this 2 by 2 block form. All right, so I can see A11, good. A21, good. A12, good. A22, and this lower right-hand corner business. We need to show that these two are equal to each other. I've got the proof. That'll be done. Okay, so what I'm going to do, I'm going to consider B equal to identity matrix, or so this is another block matrix of the dimensions needed to do the multiplication I want. So I'm going to do I's on the diagonal, 0 upper right-hand corner. And I'm going to go negative A21, A11 inverse. Okay, B is lower triangular with 1s on the diagonal. This means that B is automatically non-singular. Why is that? Because this diagonal business makes it so that I always have a 0 and a spot to make it so that nothing can be in each other's span. All right, so B times A gives me this. Okay, now think about rank. Now this goes way back. The rank of B times A is going to be equal to the rank of A because B has an inverse. It's full rank. Multiplying by a full rank matrix does not change the rank. So rank of BA is equal to the rank of A. And well, here, the rank of BA is equal to R. And the rank of A11 is equal to R. Wait a second. If I take rank of B times A, I get rank of A because multiplying by full rank doesn't change anything. Or multiplying by full rank matrix does not reduce the rank. So here, and so and I know the rank of A is equal to R. So rank of B times A is equal to R. Now, by hypothesis in the theorem, the rank of A11 is equal to R. Okay, So I know that this thing multiplied out has the same rank as A11. This means that the columns of this have to be in the span of this. Why is that? Because tacking these on, if I look back up here, all right, so this is full rank, and the whole thing is the same rank as this upper left-hand corner. So we know that this A12 has to be in the span of A11, and adding additional rows doesn't increase my span. All right, so it works out that this has to be in the span of that. Now, why do I have the 0 here? Because we've already established that this doesn't add anything to the span. So I'm just putting in a 0 because I know that doesn't add anything to the span because of the assumptions in the proof. All right, so the columns of A22 minus A21, A inverse 1, 1, and then A12 are in the span of the 0 matrix. Well, what's in the span of the 0 matrix? Only the 0 vector. That means I can only have zeros here. All right, well, that tells me that this is equal to the 0 matrix. If this is equal to the 0 matrix, then I can just go like this, and or that should be a matrix, not a vector. Add this to both sides, boom, we got it. All right, and we get corollary from this for free. Corollaries are free things we get for our troubles. If A is equal to the same block form, A is n times P with rank R, and we say that A22 is rank R also, then my generalized inverse is going to be of this format. Okay, so it doesn't matter which block we're dealing with if it's, I just need one that's full rank. Now to prove this, we just rewrite the rows and columns in the manner that we did previously, and it just works out easy peasy lemon squeezy. All right, so if A is n times P and the rank of A is R, then the rank of generalized inverse A times A is equal to the rank of A times generalized inverse of A, which is going to end up being the rank of A, which is R. So multiplying by the generalized inverse does not change the rank. Now, the generalized inverse of A transpose is the transpose of the generalized inverse. Now, A is going to be equal to A transpose A, take the generalized inverse of the whole thing, times A transpose A. And A transpose will be equal to A transpose A. Then here on the inside, I have A transpose A, then generalized inverse of the parenthesis, A transpose. And A transpose A, generalized inverse on the whole thing. A transpose is a generalized inverse of A also. Now this matrix is going to be symmetric and will have the rank of A. Furthermore, this is going to be unique regardless of which generalized inverse of the middle we use. So that's nice. So here, in general, we want to work with mathematical objects that are unique because there's no ambiguity on what's going on. I don't have to make a decision. I just have it. All right, now, if A is symmetric, then there exists a symmetric generalized inverse. But the generalized inverse doesn't have to be symmetric. There just is at least one. All right, let's look at a theorem. If A times X is equal to C has a solution, then for any generalized inverse of A, I can go generalized inverse times C, and that will automatically give me a solution. Okay, how do we prove this? All right, by the definition of generalized inverse, A is equal to A generalized inverse A. So then I'm going to say that X is any solution. All right, so here, this has a solution by hypothesis. I'm going to grab one. It may be one, maybe infinitely many, I don't know. But I'm going to grab a solution to this equation, that's X. All right, when I take this equation, I'm going to multiply both sides by X. Well, here, A times X by hypothesis is equal to C. And this is equal to C. All right, so this is C, this is C. So C is equal to generalized inverse. Okay, the negative one should not be there. I'm sorry. Oh, I feel so bad. All right, this should just be generalized inverse, generalized inverse. Please correct it in your notes. It's one of the problems with scanning. I'm sorry. All right, so now, if we consider this vector, A generalized inverse C, A, then generalized inverse to, yeah, it should be generalized inverse C. It's going to be equal to C because we have this equation. Thus, we're going to, so if I think about it, this A inverse C, that's a vector. A generalized inverse C, that's a vector. So if I take this vector and I multiply by A, I get C. Therefore, this has to be a solution to our system of equation. Therefore, I set X equal to this bad boy. Boom, we got it. Now, here's a theorem. If A times X equals C is consistent, that means there's one or infinitely many solutions, then all possible solutions can be obtained in two different ways. I can either take a specific generalized inverse and then compute this funky equation for all possible H, or I can find all possible generalized inverses and then start doing some computations. It's going to take a while, but it'll work out. All right, so next, here's our theorem. A times X equals C has a solution if and only if A generalized inverse C is equal to C for all generalized inverses. Proof. Okay, so let's think about the stupid case. The stupid case is where we have an inverse. In that case, A generalized inverse is just the inverse of A. And so then it just works out. It's stupid. This is just I, whatever. All right, so let's say that the A does not have an inverse, but it has a generalized inverse. Every matrix has a generalized inverse. Okay, so we're going to say that A times X is equal to C has a solution because we're going from left to right. So here we have a solution, and we need to show that this is correct. Then my theorem 2.8d, A times X is equal to C. That's by our hypothesis here. All right, now I'm going to multiply both sides by A generalized inverse of A. Okay, well, that is just equal to A by the definition of generalized inverse. So this becomes A times X. Well, then, by assumption, by hypothesis, A times X is equal to C. So I can replace this with C, and I get this. Boom, I've got the right-hand side. All right, so that takes me, if this, then that. Now I need to go the other direction. I need to assume that this is correct. I need to show that we have a solution. All right, so I'm going to suppose that the right-hand side of the if and only if is correct. And I'm going to say that X is equal to generalized inverse times C. We need to show that X is a solution. Okay, so I'm going to say that X is equal to generalized inverse of C. So let's multiply both sides by A. I multiply both sides by A. Now, by hypothesis, this is equal to C. Therefore, this is equal to C. And then boom, I've got my solution. Easy peasy lemon squeezy. All right, that's all I got for you. I hope you're doing well. Take care and goodbye.